Have you ever wondered how conductometry works? Conductometry, a branch of chemistry, is a fascinating field that studies the electrical conductivity of chemical compounds. It's a way we can measure how well a substance conducts electricity, giving us invaluable insights into the properties of that substance. This process is crucial in numerous scientific disciplines, from environmental testing to pharmaceutical analysis. In today's exploration, we'll delve into the theory and principles of conductometry. We'll understand the different types of conductance, specific, molecular, and equivalence conductance. We'll see how dilution affects these measurements and discuss the concept of a cell constant. We'll also get to grips with the tools of the trade, such as the conductivity meter. We'll then explore conductometric titrations and high-frequency titrations, two important techniques in the realm of conductometry. Now that we've set the stage, let's dive into the fascinating world of conductometry. To understand conductometry, we first need to grasp its underlying theory and principles. Diving into the heart of conductometry, we encounter the concept of conductance. This is the inverse of resistance, representing the ease with which an electric current flows through a substance. In the realm of chemistry, conductometry is used to measure this conductance, particularly in solutions where ions are the charge carriers. Now, how is this measured, you may ask? Well, it's through a method called the Wheatstone bridge principle. It's a clever setup where an unknown conductance is compared with a known one, and the balance point of the bridge gives us the value we're after. But it doesn't stop there. The conductance value is most meaningful when we consider it in relation to the solution's concentration. This leads us to the concept of specific conductance, also known as conductivity, which is the conductance of a 1 centimeter cube of the solution. Moving on, we encounter two other types of conductance: molecular and equivalent conductance. Molecular conductance, as the name suggests, is the conductance of a solution containing 1 gram molecule of the electrolyte, while equivalent conductance is that of a solution with 1 gram equivalent of the electrolyte. These concepts are not just theoretical constructs. They have practical implications in the analysis of solutions. For instance, they help us understand how the conductance varies with changes in concentration or temperature, offering critical insights into the behavior of ions in the solution. Lastly, we should discuss the cell constant, a crucial concept in conductometry. It is a factor that takes into account the geometry of the cell used for the conductance measurement. It's calculated as the ratio of the distance between the electrodes to their surface area, and it's essential for accurate conductance measurements. With a solid understanding of these principles, we can now explore the different types of conductance. In conductometry, we deal with specific, molecular, and equivalence conductance. But what do these terms mean? Let's start with specific conductance, also known as conductivity. It's the measure of a substance's ability to conduct electricity. For instance, silver has the highest electrical conductivity of any element, making it a champion in this category. Next, we have molecular conductance. This is where things get a bit more intricate. Molecular conductance involves the conductance of a solution per unit volume. For example, if we have a solution of salt water, the molecular conductance would be the electrical conductivity of that solution divided by its volume. Last but not least, we have equivalence conductance. This term might sound a bit daunting, but it's actually quite straightforward. Equivalence conductance is the conductance of a solution containing 1 gram equivalent of electrolyte dissolved in it. To put it simply, if we have a solution of sodium chloride, the equivalence conductance would be the conductance of that solution if we had 1 gram equivalent of sodium chloride dissolved in it. By understanding these types of conductance, we can delve deeper into the fascinating world of conductometry. We can explore how different solutions react, how they conduct electricity, and how we can use this information in a practical way. Understanding these types of conductance is crucial as it leads us to the next topic, the effect of dilution. Did you know that dilution can significantly impact conductance? Yes, it's true. In the world of conductometry, dilution plays a key role. When a solution is diluted, the number of ions per unit volume decreases, and so does the conductance. However, the decrease isn't linear. As we continue diluting, the conductance starts to decrease at a slower pace. This happens because the decrease in the number of ions is compensated by an increase in their mobility due to lesser interionic attractions. Now let's switch gears and talk about the cell constant. What is it, you ask? Well, it's a crucial factor that influences the conductance measurement in conductometry. The cell constant, often denoted by the symbol K, is the ratio of the distance between the electrodes to the area of the electrodes. It's a measure of how the configuration of the cell influences the conductance. In a nutshell, the cell constant gives us an idea about the efficiency of the cell. A lower cell constant means the cell is more efficient in conducting electricity and vice versa. It's important to note that the cell constant doesn't change with the nature of the solution or the electrodes. It remains constant for a particular cell. The cell constant, a critical component in conductometry, paves the way for our next discussion, the conductivity meter. A conductivity meter plays an essential role in conductometry. But how does it work? Well, simply put, a conductivity meter measures the ability of a solution to conduct electric current. It does this by applying an electrical voltage across two electrodes submerged in the solution. The resulting current is directly proportional to the solution's conductivity. This device is invaluable in many fields, from water quality testing to chemical analysis. It allows us to measure specific conductance, which is the conductance of a solution in a cell having unit length and unit cross-sectional area. Now let's delve a little deeper into the world of conductometry with conductometric titrations. Conductometric titration is a type of titration in which the electrolytic conductivity of the reaction mixture is continuously measured as one reactant is added. The point at which the conductivity changes dramatically is called the end point, similar to the color change in an acid-base titration. These titrations are particularly useful when the reaction does not involve a change in color or when the solution is too cloudy for a color change to be observed. For instance, it can be used to determine the concentration of a strong acid in a solution, or to find out the amount of water in a sample of ethanol. Here's a fun fact. Did you know that the conductivity of a solution not only depends on the nature and concentration of the ions, but also on the temperature? That's right. Conductivity increases with temperature, and most conductivity meters have a built-in temperature compensation to account for this. So, in essence, a conductivity meter and conductometric titrations are vital tools in the conductometry toolbox. They offer a unique and powerful way to measure and analyze the properties of various solutions, aiding our understanding of the world around us on a molecular level. Conductometric titrations, a practical application of conductometry, bring us to our last topic, high-frequency titrations. High-frequency titrations might sound complex, but they are simply another fascinating aspect of conductometry. These titrations are a unique method of conducting experiments where the frequency used is much higher than what we usually encounter. The beauty of high-frequency titrations lies in the fact that they allow us to study the reactions that occur at a rapid pace, reactions that would otherwise seem instantaneous to the naked eye. When we talk about conductometry, we usually refer to the measurement of conductance at a single frequency. However, in high-frequency titrations, we can measure the conductance at multiple frequencies. This opens up a new dimension in our understanding of chemical reactions, enabling us to gain deeper insights into their mechanisms. High-frequency titrations are not just theoretical concepts, they are used across various fields of science and technology, from pharmaceuticals to material science. Now that we've unraveled the mysteries of conductometry, it's clear to see how this science shapes our understanding of the world around us. So there you have it, a comprehensive guide to conductometry. We've journeyed through the fundamental theory and principles, understanding how conductance measurements are vital in the world of chemistry. We've explored the different types of conductance, from specific and molecular to equivalence, each with its unique role and significance. We've delved into the effect of dilution on conductance and discussed the concept of cell constant. We've navigated the technical landscape of a conductivity meter and the intricacies of conductometric titrations. The journey concluded with high-frequency titrations, a fascinating area of study that pushes the boundaries of our knowledge. Remember, the beauty of conductometry lies in its wide-ranging applications, from analyzing solutions to monitoring reactions, and even in environmental testing. The understanding of this field paves the way for scientific exploration and discovery. Subscribe for more, because you won't find me later. Until next time, keep exploring the wonders of chemistry.